now. If you remind me at the end of the class, there's one across the hall. I can go get it. All right, we're recording. Look at this guy. Brooke Taylor, responsible for Taylor series. He looks like every European mathematician ever. Yeah, pretty much. I mean, wigs were a thing back then. All right, so let's remember what a Taylor series is, and then I'm going to give you a kind of a short preview as to what we can do with one today. So let me just scroll, and you can flip back if you would like to. But remember our Taylor series, the idea of it, we did Taylor polynomials last time. So those kind of the difference between the verbiage. Taylor polynomials are going to end somewhere. Taylor series, infinitely many terms. So these are good at approximating. Today, we're going to be finding a Taylor series that's actually equal to a function. So we're going to actually memorize 3 of them for sine, cosine, and e to the x. And we're going to be able to kind of build off of those without having to do this process of like taking a million derivatives. So we remember we had our kind of each term had the nth derivative wherever over n factorial x minus our center to the n. So we also had this formula for our coefficients. That's kind of just what I said without that x minus the center to the n. So I just want to practice writing one of those one time and then give you a preview of some of the things we can do today. This is actually a pretty good, darn good warm-up question for our notes for today. So we're going to write the 3rd degree Taylor polynomial about x equals 3. Tell me anything you know based on the directions I just read out loud. The center is 3. Thick. All right. Anything else you learned? All right, 3rd degree, that means 3 derivatives. That's helpful. What does that mean about my last term? That's kind of a vague question, but it'll have a 3rd derivative. It'll also have the power of 3. So we're going to end with cubed. All right, so I'm going to call this, I don't like writing in red, but I'll just go back. All right, so p sub 3 of x, that's just fancy way to say a polynomial of the 3rd degree. X is my variable. So what's the first term? -4. Is it just me and Connor in here today? Oh, okay, cool. The person that was participating in my Algebra 1 class sat there too. Nice. Magic chair. All right, does anyone think they know anything about the next term besides Connor? Which derivative am I going to use? The 2. And then this is our linear term. So we need an x in here. I'm going to say it's x minus something. 3, good. All right, to the 1st power. All right, what about our next term? Good. All right, we remember when we get to the 2nd degree term, we need a 2 factorial. What derivative is going to go on top of that? The 2nd derivative, which is, oh, you said 7. Sure, just pretend. Yeah. All right, what goes on here with the x's? X minus 3? 2. Notice we have 2nd derivative over 2 factorial 2nd power. It all matches. Yeah. Yeah, pretty much. So if you missed this day of class, essentially what this is doing is this first term is matching the y value. Then we're matching the slope. We're matching the 2nd derivative of our guy. So it's giving us a better and better approximation. All right, am I done? No. All right, tell me about the next term. Beautiful. Perfect. No, so that's a good question. Here, since this is a Taylor polynomial of 3rd degree, we are going to stop there, full stop. Today, we're going to add on that plus ... Now, we talked a lot when we did this class about how annoying it was to have to find all of these derivatives. So I could be given them, but like if I had to do sine of x to the 5th degree, I just have to start taking derivatives. So the cool part is that Taylor polynomials are polynomials. A lot of the rules that we want to do in algebra work really well with polynomials. So here's an example of what I could do. I like to think of Taylor stuff as like it kind of does what you want it to do. So looking at this, it's telling me to write a fourth degree. What's that tell me? What does fourth degree tell me? All right, we're going to end in a power of 4. About x equals 0. What does that tell me? The center is 0. What's another way to tell the center is 0? If it's a Maclaurin series, a different Scottish mathematician. Now let's look at what function they're trying to have me do. They're trying to have me do a function g of x equals f of x squared plus 3. That feels a little awkward and weird. Partially because if I have to go and take 4 derivatives of that, I see the first one's going to have a chain rule, which is going to cause the second derivative of that to have a product rule with another chain rule inside that. I'm not feeling great about just taking derivatives of this guy. But we just did one for f of x. What does it look like they're doing to f of x to get g of x? Kind of a vague question. What does it look like they've done to get from f of x to this? Okay, so it looks like they're doing something to the inside. Would you agree with this statement? It looks like they plugged in x squared plus 3 where x is. All right, I'm going to try to do that. Substitution is something that's legal with polynomials. So what I'm going to try to do is take this, but I'm going to plug in x squared plus 3 everywhere x is. Now that feels a little weird because our center was 3 before. Now they're asking me for a center of 0. We're just going to trust in the process, trust in the idea of polynomials. Yes. Thanks. I was going to write that down. I forgot. All right. So let's try. The first term, nothing's going to change. There's no x's in it, so I'm just going to keep -4. All right. The next term, instead of x, to be really, really clear, I'm going to write x squared plus 3, and then I had -3. Well, let's look at that. What's going to happen to those 3's? 0. They're going to cancel out. Then I'll just have x squared. Is that what a term should look like if the center is 0, just like x squared? Yeah, that's actually really convenient. All right, let's try the next one. 7 over 2 factorial. I'm going to again plug in x squared plus 3 minus 3 squared. All right, should I do the next term? Ooh, someone said no. Why should I not do the last term? It's a 4th degree. With what I have right here, do I actually need the last one? Let's look. Is x squared squared x to the 4? Yeah. So I'm gonna write myself a note here. So I'm gonna do the last one and just cross it out so we can reference this on our notes. But effectively, what's going to happen is we don't need this last term because this one, what degree would this last term be? How do we do exponents? Yeah, this would be x to the 6. X squared times x cubed would be n. So this guy is not needed. So our actual I guess I can call it Maclaurin, but Taylor polynomial, 4th degree, would be, ooh, that's an ugly plus sign, plus 2x squared plus 7 over 2 factorial x to the 4th. So that's one of the very many ways we can take a Taylor series we know about and turn it into one that's kind of building off one we have either memorized or we've already created. So we're going to very much extend this idea today in ways that are more difficult than this, more interesting than this, and we're going to be doing it with infinitely many terms instead of just like 3. So what I would like to do here is just pause for a second to do a very, very easy notes check. So the first question is going to look just like this one. The second question, I'm just going to scroll back to show you, is going to ask you for a specific coefficient. So it'll be kind of like this question on the front where we pulled the coefficient of a certain term where we had to take the derivatives to get there. I'll be passing these out really quick just to get you to practice with this formula before we kind of go ham and really change the game here. So these ones are super similar to each other. Feel free to work with someone around you. We'll take probably only like 5 minutes to do this. You don't need very long. I'm going to put up a vocal environment. It's in like math somewhere. All right, I'm gonna put up a hopeful 5 minutes. The first one's super easy. I mean, it's like a 6 degree, isn't it? Yeah. Just make sure your terms are matching. You should have whatever factorial, whatever derivative, whatever power, all of those match numerical value. Mm-hmm. Oh, yeah. Yeah, we're generous. Oh, yeah. Yeah. That was really fun. Oh, yeah. So you're just trying to find the coefficient of x cubed is going to be like this guy right here. Just trying to find the either see the third derivative. Hello. Yeah, I like that. Oh, thank you. Can you not have an x in there? What should x equal? Not x. Where'd your e's go? What number should you be plugging in for x for the e's? The center. So our coefficient should be a number.
Okay. So does this look right?
I think so.
Okay.
We
Hi.
have to simplify the coefficient, right?
Perfect. Make sure for the second one, your coefficient should be a number. So you should be plugging in something for x. So you should be the third one. All right. On one hand, how many more minutes do you need? All right. I see 3s and 5s, so let's go with 4. The second one's much shorter. Alright, so for this guy, you're thinking like this the third derivative. Right? Plug it in the center, that should be the point here.
Oh, so you don't take the third one.
Right, so you're working with this. What x value do you Yeah. You just don't need to write out. Yeah.
Yeah, you were looking off the line.
That's fine. Just make sure you leave on course.
Am I supposed to have like another?
Yeah.
I'm confused about this.
All right. So I was okay.
Yeah.
So for
Like
that's all right. So yeah, it's gonna be a lot like this one. So what you're gonna do, you're looking for the coefficient of x value. So think like in your x, like it's not the one of these ones. It's like the third derivative over 3 factorial. So you that's fine. So you're thinking the third derivative over 3 factorial. So I need to find the third derivative of this. Plug in an x value. Plug in an x value, and you're gonna go over 3 factorial. So I'd start by taking 3 derivatives. Hello.
Is this correct?
Plug in a number. I can bring it up.
So starting with your absolute that's 3. I use 25.
So I just need a coefficient, and there should be a number. So don't use this part, and the number should be in there for the x. Why is it Sorry. You don't want this part. You want, instead of putting your 7 in there, I want it up in the x. Also make sure you do 3 derivatives, not just 2. Perfect.
Oh, because I rewrote it.
Oh, perfect. Oh, I didn't grade those yet. Don't Did you draw?
And then notice I
You could, yeah, you could simplify the exponent.
like this there. So why like put it back in? That is gonna add. Yeah, that's the cool. So which part? The other one is- Okay. Actually, you
Oh, and you had the quiz review for Ethan probably there.
All right, what I'm gonna do, I'm gonna walk around with new notes. If you still have your notes checked, I would love to trade you for it. We won't be doing another notes check today, partially because I don't think we're gonna get all the way through these. But if we do, what a magical burden we'll have fun. This is like one of my favorite sections. It's just fun. It happens. Okay, I think, there are different tests. One has a lid. Are you getting your test? You want to
Try this.
that has been
Go to the first one. Oh, I don't know.
How did you go from 3 to 8? So you're just right.
All right. Do I hand you guys notes? Yeah.
And you want me to grab your paper?
All right. So let's start to talk about what we're doing today. So again, the motivation behind what we're doing today is let's try to find a way to find these Taylor, in essence today, Taylor series, where, where I don't just have to take a million derivatives. Now we do have to do a little pre-work for that because the ones we're going to build off of, we're mostly going to build off 3 Maclaurin series. The Maclaurin series for e to the x, the Maclaurin series for sine x, and the Maclaurin series for cosine. We actually looked at the one for sine of x already, if you remember it at all. If you don't worry, we're going to figure it out again. I'm definitely making my notes for reference today. There's a lot happening. All right, let's do e to the x first because he's the easiest. He's the easiest to remember and memorize. When I say memorize, I actually do mean memorize. We're going to need to have these in our brains. Luckily for us, these ones are relatively easy to remember. There's lots of patterns to the point where I gave these notes to my one of my Algebra 1 students a couple years ago, and he came back and almost had them memorized. So lots of stuff. Now, you'll notice there is a difference, kind of going back to Nicole's question from earlier, of Taylor polynomial versus series. Notice that the polynomials stopped. They had a certain number of terms, and then we were just done. Here, this is a Taylor series, so this goes on forever and ever. If we think about how we constructed the polynomials, we had that our y value matched, our first derivative match, our second derivative match. If we take this out forever, that means every single derivative matches with the original function. So one cool thing that's going to happen is these Maclaurin series, if they go on forever, are actually going to be equal to e to the x. So if I graphed this series with infinitely many terms, graphed e to the x, they would be the same function, which is pretty darn powerful. So let's find the one for e to the x. We're going to hope we can find a pattern so I don't have to take infinitely many derivatives. So you guys ready to help now? All right, so if f of x is e to the x, what's f prime of x? Thank you. That was a little nerve-wracking. What's f double prime then? How about F triple prime? All right, I feel like I'm seeing a pattern. What's the center of the series that I'm trying to write? 0. How do you know? It's a Maclaurin. Should we look up his picture too? Remind me when we're done with this one. What? We looked up Brooke Taylor's picture. Brooke's a cool name. And he spells it like a brook. Those British guys. All right, so I'm going to plug in 0. And Maclaurin is Scottish. It sounds Scottish. What happens when I plug in 0? Ah, that's very nice when we're thinking about writing these. All right, so let's try to write out some terms. We are going to try, and this is very similar to how most of your free responses about Taylor series will be constructed. Notice we're not using sigma notation. That's very purposefully because we can do a lot more things with our general term that way. We're going to try to write kind of the first 4 terms and then the general term. This guy right here would be known as the general term, very similar to like the nth term of our series. We want just a term for all of the terms. We could plug in something and find it. So what would the first term of our Maclaurin series be? 1. They wanted the notes this morning so they could find patterns because they didn't want to factor this morning. So 1. Yeah, we were factoring like when a is not, or when a equals 1. So like x squared plus 5x plus 6. Only graphing. That's great. All right, what's the next term? All right, plus 1 times x minus 0. I'm just going to call it x. All right, what's the next term? 1 over 2 factorial times x squared. I'm going to write that x squared over 2 factorial. Sorry. All right, what do you think I'm going to write for the next one? 1 over 3 factorial times x cubed. I'm going to write it x cubed over 3 factorial. Okay. Okay. All right, I think I see a pattern. Do you think you see a pattern? What do you think the general term, the nth term, is going to look like? Like that? Beautiful. Plus dot, dot, dot. Now, let's talk about this. This is true. So I'm gonna tell you the interval of convergence here, aka the domain. This is true everywhere. And when I say this is true, these two things are equal to each other. So I plug in x to this side, I plug in x to that side, I get exactly the same number no matter what x is. That is crazy. Yes. Just write it how I'm writing it. It's an interval. Let's write it like an interval. Yeah. So that was 1 for my first derivative over 1 factorial if you want x minus the center, x minus 0. Yep. All right. So let's go ahead and I want to now find the one for sine of x. You ready? All right, this one's a little bit more interesting. I think we can figure it out, though. Oh, yeah. The reason we're probably not going to write these as a sigma notation, you could write this or not write this. We would put our general term in here. These get really weird with the index, the starting index here. So to get the 1 as our first term, we have to start with n equals 0. We're going to end up taking derivatives and integrals of these that can really mess with that bottom index. Sometimes you take the derivative, the first term goes away, you got to adjust your index. So one way to get around that is to just list the terms because then you don't have to like declare what you're starting with. So I'm just going to need you to trust me that even though it's a lot of writing out the first 4 terms in the general term is going to make you make less mistakes. All right, can you for me? I would like you to do, we've actually done the next one, but I want you to do it again. I would like you to find me, let's try 4 derivatives. I think we can get it in that. I want you to try to find the first 4 derivatives. No, I lied, 3 derivatives. And plug in what you think the center is to all of them. Should not be too terrible. Is anyone else warm? I feel like this room is really warm. Sorry if you weren't, and we pointed it out, made you warmer. Yeah. What?
Is the X, would that just have been like the center? So would that just have
So then like x minus 0, which is why you don't have like,
what about this?
that's your first derivative, so those were all ones.
Oh, 1 times X.
Mhm. You guys have 4 derivatives already? Yeah? Oh, you have 3? All right, what's my first derivative of sine? What's the next derivative? What's the next derivative? What's the next derivative? Yeah, it's just cycles. All right, what should I be plugging in? What's my center? How's your unit circle doing? Warning, 10-3. When we get to unit 10, please know your unit circle. Just chucking it out there. That's our second to last lesson, though. Make it as easy.
Can you teach us these?
No, I literally can't. You guys are gone after the AP exam, so. All right, I know, it's been a long time, girl. All right, what's sine of 0? What's cosine of 0? What's negative sine of 0? What's negative cosine of 0? Wow, all right. So let's talk about writing out these terms. Now, when I write out a Taylor series, unlike your notes check where I said it was okay, here I don't want to write terms that are 0. I just don't want them there. So when we write our general term, we're also going to write the general term so that it reflects the fact that we don't want to write the terms that are 0. So will I have a constant term here? Will I have a number at the beginning? No, because that f of 0 is 0. So the first term I'm going to have has my linear stuff in it. So I think that's 1 times the quantity x minus 0, 1 times x, x. All right. Will I have a x squared term in here? No. Will I have an x cubed term in here? Yes. The derivative is -1, so it'll be minus, I'm going to do x cubed over 3 factorial. All right. Thinking that these derivatives cycle, will I have an x to the 4th term? No, I'm not going to have any even terms. That's a good notice there. Will I have an x to the 5th term? Will it be positive or negative? All right. It's going to be x to the 5th. What do you think the factorial is? Wow. Y'all are brilliant with your pattern making brains. I want to write one more term. What's the next term going to look like? Beautiful. All right. Now, the problem, I want to write a general term. When I'm writing this general term, I'd like to be able to plug in 1, get x. Plug in 2, get x cubed over 3 factorial. Plug in 3, get x to the 5th over 5 factorial. So that's a little bit more complicated than it was before. Let's talk about one thing that I notice about these terms, though. Does anyone notice? This is a very, very big question. I'm hoping someone's reading my mind. Does anyone notice anything about these terms? Starts with the letter A. They're alternating. How did I make terms alternate? There we go. -1 either to the n or n plus 1. Now, usually we want this to start at, I kind of lied. I usually want this to be like the 0th term. That's how they write them. So if that's the 0th term and it's positive, do I want n or n plus 1 in the exponent? So if the first term is n equals 0 and it's positive, do I want n or n plus 1? So that it would be -1 to the first and make it negative? You hooligans. Let's do -1 to the n. That way when I plug in 0, that's -1 to the 0, which is +1. All right, let's see how brilliant you are. I need to put something down here that will give me odd numbers. I actually did it a couple classes, or no, last class, when we had that thing where it was like only odd powers. So I need something that goes here and here, so that when I plug in 0, I get 1. When I plug in 1, I get 3. Take your test. When I plug in 3, I get 5. When I plug in 4, I get 7. Does anyone have 2n plus 1? Let's see if it works. Let's see if it works. All right, plug in 0 to 2n plus 1. 1. Plug in 1 to 2n plus 1. 3. Plug in 2 to 2n plus 1. Plug in 3. Does it work? Yes. So that's a really great way to do odd numbers. All right. What's missing from my Taylor series since it never ends? Plus dot dot dot. All right. I erased the 4 because I was writing too big. But this, again, our interval of convergence for this, everything. So if you hated sine of x, here's an alternative way to write it. An infinitely long polynomial. You're welcome.
Wow.
You're welcome.
Can I just write like x to the third of a 3 dot dot dot?
Depends on my directions. My directions are usually going to say, give me the first 4 terms in the general term, because that's what the AB test always says. All right, now, who's tired of taking derivatives? All right, so I am just sick and tired of finding Taylor series this way. I don't want to have to take 4 derivatives, plug it in full time. That's silly. Let's get a better way to do this. Can anyone think, again, a vague question, hoping for a specific answer. Can anyone think of a calculus way to get from sine to cosine? Take a derivative. Beautiful idea. Well, aren't polynomials really easy to take derivatives of? Like x, x cubed, x to the 5th, those are super easy to take the derivative of. This is a legal thing I can do. So let's see if we can do it. All right, so we're going to take a derivative. All right, so we're claiming that cosine of x is the derivative of sine of x. I mean, cosine eventually is we're going to have it memorized. We will take the derivative of other series, though. All right, so let's take the derivative term by term. It's actually a really good setup when we have it written out like this, because we're going to get braver and braver and braver. And by the time we take the derivative of this, we're not going to be scared anymore. So, what? You owe me a round 2. You still owe me a round 2.
I can grade your test as is.
All right, who's feeling brave? What's the derivative of x? 1. We don't need dx, just normal derivative. All right, I'm just going to keep the factorials for a second, see what happens. What's the derivative of x cubed? Ooh, looks like something cool is going to happen with the 3 and the 3 factorial. We'll get back to that. All right, I'm going to keep the 5 factorial. What's the derivative of x to the 5th? 5x to the? Cool. We're going to simplify it before we write it in the box, if that matters to anyone. All right, what's the derivative of x to the 7th? Wow. All right. So let's look at what we did. And again, kind of like last class with the interval of convergence, we're going to remind ourselves what the variable is here. So what am I taking this derivative with respect to? Yeah, I'm taking it with respect to x right here. So when I take this derivative, all of those n's are going to act like constants. So I'm going to keep, the alternator seems to just be like doing its thing. And on the bottom, I'm keeping this factorial the same because I'm going to work with canceling it later. Let's look at what the power guy is doing. So I had x to the 2n plus 1. What do you think the derivative of that is going to look like?
Wow.
All right. What do you think the derivative of x to the 2n plus 1 is going to look like? 2n plus 1 is going to come down. X to the 2n. Why is it just 2n? I subtracted 1. All right. I think these factorials are going to do something cool. So I'm going to make myself a little bit of scratch work right here for these three, and then we'll try to make a prediction. What does 3 factorial mean? Would you agree with me that this 3 is going to cancel with this 3? Okay. Yeah, that is 2 factorial on the bottom. Let's see if that works. What's 5 factorial? That was speedy. All right. I think these 5 factorial, or the 5s are going to cancel. And then what would be left over? 4 factorial. What do you think is going to cancel in this 7 over 7 factorial? What do you think is going to be left over? All right. So let's try to write this out. Cosine. 1. Feeling brave. All right. Thoughts on next term? Love it. That's a weird 2 that I wrote, but I kind of like it. All right. Next. Ooh. I made someone like literally storm out of my classroom because I wrote an entire line of something as big as this with one type of 2, and the very last one was different. This exponent has a curve. Oh, speaking of the general term. All right, speaking of the general term, what do you think the general term is going to look like? Okay, I want to simplify it though. All right, what's going to cancel out? The 2n plus 1. So I think the alternator stays, right? I have the x to the 2n, and oops, forgot the 2 for you guys. What kind do you want? You're welcome. All right, and then what's going to be on the bottom? 2n factorial. All right, couple of reasons why. Yep, so I could do here, I could break this down into 2n plus 1 times 2n factorial, or you could pattern make here. What kinds of numbers are at the bottom here? Even. How do I represent even numbers? 2 times something. So you could pattern make there to make sure. This again is true for all numbers. So for all x values from -infinity up to infinity. So I think this is one of the coolest things that we do. These functions are actually equal to each other. I have to make my polynomial infinitely long, but if I do, I get something that's actually equivalent. It's pretty darn powerful. So why would we spend all of this time building up these 3 series? Eventually, hopefully soon, you're going to have these 3 series memorized. Now, there are patterns. You have sine and cosine. What patterns do you notice? Sine is odd, cosine is even. That happens to be the same as the graphs. If you think of like even and odd graphs too, sine is odd, cosine is even. Both of them alternate, which is helpful. What about e to the x? What do you notice about that one? Yeah, it has all the powers in it, and it doesn't alternate. So these aren't super hard to memorize. They do have a lot of patterns. Yeah, Sydney. Yeah, so there are lots of really cool things you can do to combine these series. So what we're going to spend the rest of our time doing is trying to combine these series in fun ways. So what can we do to manipulate these series? Well, we saw at the end of the 9.1 notes, we saw how we could substitute something in the series, and we're going to continue to do that. We could multiply or divide. We can multiply by a constant, which is easy. That's kind of just like distributing. We could multiply a variable, also like distributing. I could multiply two series together. We will do that. We won't do it for like an infinite number of terms. You might have to get like the first three, because that's like distributing infinitely many terms into infinitely many terms. It's very exciting and very cool, but also a little bit hard. We could add or subtract, so kind of like Sydney's question right there of could we add two series together to get all the terms in e to the x? Absolutely. And then we kind of just saw when we were doing sine to cosine, we could differentiate, so take a derivative, or we could integrate. Now, I'm going to highly recommend, kind of like we were doing here, you're going to want to be okay with writing stuff down. These questions aren't that hard, but they look terrifying because of the amount of stuff that we have to write down. Just trust yourself and take it term by term. So I'm going to show you how I would do these questions. Highly recommend. I'm doing them this way because it's the easiest way, I think. So we're going to find a Maclaurin series for sine of x squared. Does that look like one of the three series from the front of this page? Yes. Which one does it look like? It looks like sine of x. And it looks like I took sine and I plugged in x squared where there was an x. Yes? So that's exactly what we're going to do. Notice these directions, kind of going back to some of James's questions earlier, asked for the first four non-zero terms and the general term. That's basic directions for pretty much every question like this you're going to get. So how would I do this? I would start, why did that just adjust where those were? Well, I don't like it. Oh no. Okay, so I'm going to start by writing the first four non-zero terms and the general term for sine. Because normally if I were doing this question, I wouldn't have the front page to go back to. Anyone remember what the first term of sine was? No. X. Oh, it's going to keep doing it. I don't like it. No. Oh, it's so terrible. But it's hard to write. It's hard to write. Oh. It's just adjusting it to a different location. Ah. Oh my God. Ah. I don't like it. All right. Did you ever want to watch your teacher have a mental breakdown over nothing? Welcome to class. All right. All right. So I'm just writing down the one from the front page. If I write fast enough, maybe it won't do it. All right. So this is the one we have memorized. I would like to just write it down so that I have all of the terms. So notice I have my first four non-zero. I've got my general term. Now, what it looked like it did was it took this x, wherever there was an x, and it made it an x squared. So I'm literally just going to do that, simplifying ever so slightly as I go. So I'm going to find f of x, which is sine of x squared. Oh, instead of x, what's that going to look like? Wow. All right. Now, x cubed. If I'm plugging in x squared into x cubed, what do I do to those? Gave it away. What do I do to those exponents? I multiply them. So I'm going to have x to the 6th over. Is the factorial going to change?
No. Yes.
Add is like x squared times x cubed. So this guy is like x squared times x squared times x squared. So x, 6 x's. I said x, 6 x's. That's how we do it in Algebra 1. No. All right. What's the next term going to look like? All right. So x squared to the 5th is x to the 10th over 5 factorial. What's the next term going to look like? Ooh. All right. We're skipping some terms. Going to the general term. So let's think about what changed, what stayed the same. For the general term, is there anything that's just going to straight stay the same from what it was before? All right, the alternator. Anything else going to stay the same? The factorial on the bottom. Notice we had like 3, 5, 7, still 3, 5, 7. So this is still going to be 2n plus 1 factorial. What is the top going to look like? Okay. What would I do to those exponents again? I would multiply them. So let's think of multiplying that exponent by 2. What would the exponent look like? Perfect. Got to distribute that plus dot, dot, dot at the end. So notice none of those steps was particularly like horrific. Really all we're doing is using some slight exponent rules and taking it term by term. I really like writing the series this way. Not only does it get you your points very easily because we're following directions, but I like the bravery aspect. I get to start with easier terms and work my way up to that general term.
Why were you squaring it besides the negative?
Because I was plugging in x squared where x was, not like squaring the term. So here, this guy right here is like x squared cubed over 3 factorial. So that squared isn't interacting with the actual negative sign. It's just interacting with where that x was. Good question, though. All right. So here's a way that they could be constructed on the AP test. That might be part A, and part B might be to take the derivative. Oh, we are almost out of time. Let's go ahead and just take the derivative, and then I'm going to ask you a scheduling question. All right. So we got a couple terms to work with. We're just going to take the derivative term by term. This is a polynomial. That's how we take derivatives of polynomials. So let's start with the easiest one. What's the derivative of x squared? Sorry, of just this guy. 2x. All right. The next one. Well, let's just keep the 3 factorial. What's the derivative of x? Yeah, I could simplify that. I don't want to. I'm not going to have to use this later on. All right, I'm going to keep the 5 factorial. What's derivative of x to the 10th? All right. Oop, next one's negative. All right, 7 factorial, top. All right, we're feeling brave. We got it. Yeah. All right, is this derivative going to do anything to the alternator? Does the alternator have an x in it? No. So -1 to the n. Are the factorials in the bottom going to change at all? No, they are not. They don't have an x in them either. 2n plus 1 factorial. All right, what is the derivative of x to the 4n plus 2? Beautiful. What am I missing? What? It's notation. Plus dot, dot, dot. All right, scheduling question. Let me pull up my calendar. All right, so can I have your attention? What even is 9.4? All right, so we obviously did not get done with those notes. I am pondering a kind of like Unit 9 review day. Mostly, I want to know where you would like that to happen. So I could finish these notes next time and just give you the rest of the time to work on your problem set. I could keep doing like half notes and picking up stuff and using that review day towards the end of the unit. Where are you feeling like your preference would be for like a stop and work on stuff?
Yeah,
As close to the test as possible? I can hear that. What? Yeah. All right. So what I'm leaning towards, just to be very like upfront, is I'm leaning towards trying to do it between 9.4 and 9.5. So next class, bring these notes back. We are going to finish them and we'll probably start 9.4. Bring your problem sets to every class. Thank you for your hard work. Sorry for taking too long. You guys are the best. I'll see you later. Yeah. Oh, no. It's by the door if you want it. Yes. If you want your problem set on the way out, I will have it here. If you don't want it, then don't take it. I have been.
Round two is gonna help though. I doesn't change the value. Yeah, it's. Oh.
Miss Ashley,
Ma'am.
tomorrow I have my clinicals again. Are you of your planning block the last day, block of the day?
I do, but I have like several meetings. I can probably set you up to take a test if that's what you're coming in for. But
No, I was just gonna ask you that, but.
yeah, I have I think at least 2 meetings tomorrow. Yeah, that's fine. Mhm. Okay.
Maybe I'll email you. and we can
Yeah,
find
shoot
it.
me an email and we can figure it out.
And I was actually gonna ask if I could come in tomorrow at 8. I'm working on the problem and the review, and then I
will
was probably okay. And then I was hoping on Friday.
What's your name? Let's submit it half done.
But like, I mean, not half. I just don't
Okay.
understand 2 questions. I mean,
All right, I will highlight this, figure out when you want to do round 2.
next class, possible.
Oh, yeah. Will you be ready tomorrow?
I think so. Yeah.
Whose phone is that? Yeah.
I'm coming for I'm up on boardwalk.
Today?
Yeah.
Okay. Come as soon as you can because I got to be somewhere at 2:45.
And then I was gonna ask on Friday if I could come in maybe like 8:15 and do the quiz.
Yeah.
Okay.
Bye.
I have too many things on the table.
All right. I'm just going to assume. Oh, I want these. I want these. Don't want these anymore. Oh my goodness gracious. What? Wow. Those are some cool. Where did I put? Oh, I have so many papers. Oh, I guess I can turn this off now. Please.
Stop.